And we're on question 2 on our second practice exam, which is don't pop my balloon animal. So I'm tired of being a material scientist and a polymer physicist, as I'm sure maybe some of you are as well at the end of this class. No, you all love polymers. But instead, I'm going to start a new lucrative business being a clown. I'm going to make balloon animals for kids' parties. So I'm not really too good at this point. I can only make an anaconda to scale with a length of 25 feet. My diameter is equal to 1 foot, so my radius is equal to 6 inches times 0.024 to convert to meters. My thickness is equal to 0.01 meters. So right when I hear diameter and thickness, or radius and thickness, I'm going to go ahead and make sure that we see, or hopefully we're in, a thin-walled pressure vessel problem greater than or equal to 10. So let's go ahead and solve for this problem. So my radius is equal to 6 times 10, or 6 times 0.0254. My thickness is equal to 0.01 meters. So R divided by T, 15.24. Excellent. Once I know I'm here, I don't care what the rest of the problem is stating. I know that I'm going to have my anaconda look like this. And I'm going to say that my coordinate system is 1. Actually, I'm going to call this 1 and 2. So my stress tensor is going to look like this. Sigma L, longitudinal, sigma hoop, everything else is 0. I also know that I'm dealing with a balloon animal, so that is a polymeric material. So my Young's modulus is going to be equal to 1 GPa. Actually, let's go ahead and hold on this for a second. My nu is going to be equal to 0.4. My hoop strain, 1 E times sigma hoop minus nu sigma L. Longitudinal strain will be 1 E times sigma L minus nu times sigma hoop. And I also know that I am going to have my sigma hoop is equal to delta P R over T, and sigma L is equal to sigma hoop divided by 2. So let's go ahead and, again, write some of these values in here. So sig H is equal to del P times R divided by T, sig L, let me pull this up, sig L equals sig H divided by 2, and then I could write some of these other values. We'll write those other values later, but nu is equal to 0.4 for sure. All right, so let's go ahead and see what the problem is asking. So I'm struggling kind of financially. I need to make sure that I don't plastically deform my material. That way I can reuse the material for future parties. You know, very stingy, very cheap balloon clown, but times are tough. I need to make sure blowing up my balloon takes a significant amount of strain. I need to basically blow it up. I need to strain at least 100%. So what will be the best candidates for my balloon material? Well, looking at these curves here, at 100% strain, all of these have yielded with the exception of my black curve right here. And I can also kind of estimate, let's go ahead and look at it. Let's look at this line right here. I'm just going to say that at about 1.5 megapascals, so my stress is equal to 1.5 MPa, and that occurs at about 100% strain. So that's going to be a value of 1. I'm going to have, so my Young's modulus for this problem, for this very, very particular polymer material, is going to be 1.5 megapascals. So stress divided by strain, those are going to be those values. So let's go ahead and write that out. So my Young's modulus, y is equal to 1.5 times 10 to the 6th. Excellent. So I need at least that. So it must be the black curve because I don't want to plastically deform that material. I need to reuse it. So what will be the maximum amount of pressure that I will have to blow into the balloon animal? Write out the stress and strain tensors quantitatively. So we just said in the previous problem statement, I need to at least, the very minimum, blow 100%. So I need to figure out what is going to be the strain at that, or the maximum. If we look at these expressions, let's look back. The maximum amount of strain that I'll kind of experience is I want to make sure that I don't, again, yield my material. So I need to pick that for the hoop strain, I need to make sure that we don't exceed that value. So this hoop strain is going to be the larger value each of these times. You could try to push it here, but you might get into this other region. So to be conservative, I need to make sure that this is equal to 1. So let's go ahead and solve for these unknowns in this problem, specifically for the del P. So I'm going to solve and write out that my 1 is equal to 1 divided by y times sig h minus nu sig L. I want to solve for del P. So that's going to be my del P right here. Solve that right now. set that equal. Now I can figure out my sig h. Sig h equals this, sig l equals this, and my EL is equal to 1 divided by y times sig l minus mu times sig h. And that will be smaller than that value, significantly smaller, as you can see right there. So you could see the danger. If you solve this the other way, you could definitely get into a scenario where you're plastically deforming the material. So we need to make sure that our hoop strain is not basically is not the value. Now you could also solve this problem, again, kind of choose your own adventure. The material seems to kind of yield around this, possibly around this like 200 value of strain. So you could really try to push it to the limit, but let's be safe and let's save our breath essentially as too. All right, that is our full stress strain tensors quantitatively. My lung capacity will only allow me to blow to 100 megapascals of pressure. Will I be able to make my balloon animal? So this is 123 kilopascals. So absolutely, my lungs will definitely let me do it because I need to reach at least 123 kPa. Great. What's my rotation to get to principal stress state? I'm already in it, 0 degrees. What about for principal or shear stress state? 45 degrees. And then finally, some annoying kid asked me to calculate the stress state in a plane of both the hoop and longitudinal stress. So let's look at our stress tensor, just here and here. So we said that this is this. So he's asking this very interesting child at this birthday party that's interested in continuum mechanics and rotational stress tensors wants the basically in this plane we need to figure out what is the stress state 87 degrees from the principal stress state. So we already know that we're in the principal stress state, so we don't have to figure out any rotation from that. So instead, all we have to do, I've evaluated this already, so I'm going to call this my stress in the 1-2 direction. So sig L, sig H, 0. I'm already in that principal stress state, so now all we have to do is just do T stress 1-2. So we're in the principal stress state, so we're rotating. We need to see when theta goes to minus 87. Why minus 87? Because this problem says counterclockwise, or excuse me, not counterclockwise, clockwise. That is a negative rotation. So that's it. So that's the value that you'd get. And if you wanted, for example, the maximum shear stress value, T dot, this is just a fun, you don't have to this is just extra. So if I asked you for the maximum value of shear stress in this plane, so if we rotate by 45, let's check that this answer is correct. Sig H minus sig L. I want to divide this by 2 for this particular plane. Excellent. Always nice when answers match. So be ready to kind of do some of these problems during your exam, and I will see you all in the next video when we get into some composite mechanics, and specifically my dreams of mashing home runs in the Little League World Series. I'll see you all in the next video. Thanks. Bye.